I want to prove a couple of theorems. They're pretty easy, and let's look at them. So for any vector space V and W, and T is a linear transformation, then T T right T of 0 is always equal to 0. Now this could be the zero vector in V, that could be the zero vector in W. That's fine, but it's always going to happen. Why is that? Well, first we note that the scalar 0 times the vector V is always equal to the zero vector. We established that a long time ago. Now, let's look at T of the zero vector. T of the zero vector, well, the zero vector is equal to 0 times any random vector V. And I could pull out the 0. That's one of the properties of linear transformation. And now I have a scalar 0 times this new vector. This is a vector in W now, by the way. But 0 times this vector is now the zero vector. Of course, that's a zero vector in W. Originally I started with the zero vector in V, but that's the way this theorem works. So that's number one. Number two, I'm not even going to bother proving. I think it's pretty self-explanatory, which is that if T is a linear transformation, so if I take C1 V1 plus C2 V2 plus Cn Vn, meaning some linear combination of a bunch of vectors, that's going to be equal to C1 times T of V1 plus C2 times T of V2 plus dot 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 plus Cn times T of Vn. And that pretty much goes, I think, is self-explanatory. But I want to use those theorems to, or at least the last theorem, to prove a fact, to prove a problem. So T is a linear transformation from R3 to R3. This is an example. And T of 1, 0, 0 is this vector. T of 0, 1, 0 is that vector. T of 0, 0, 1 is that vector. Notice that these three vectors here are the bases, or it forms a standard basis of R3. That may or may not be very significant, but I'm saying it. Anyway, what I want to do now is use this information here to find the linear transformation of 2, 3, -1. So I want to use these three. Well, first we say that the vector 2, 3, -5 is equal to 2 times V1. V1 is that guy right there, plus 3 times V2 minus 5 times V3. We see that that's pretty easy to see. And therefore, T of this is equal to 2 times T of V1 plus 3 times T of V2 minus 5 times T of V3, which is equal to 2 times this vector, 3 times that vector, minus 5 times that vector, which comes out to a grand total of 12, -17, +17, and that is the answer. Yay!